Let's now move to the scheduling for interactive systems. So this is a list of scheduling strategies. These are discussed in the book. We are going to go through 3 of them. So let's start with round robin. We begin by defining a quantum, so a time interval during which the process can run. With round robin, the idea is that we let each process run for a while, okay, and we just go in a round robin fashion, as the name suggests. So we take process 1, then process 2, then process 3, that is, we take them from the queue of ready processes we have. And whenever we start executing a process, we let it run for a certain period of time, the quantum. After that, we stop the process and we schedule the following one. It's simple to implement. You just keep a list of ready processes. What is challenging here is to identify the right length for the quantum. If you take quantums that are too short, then you have high overhead because you have to do a lot of context switches frequently, so you're wasting resources many times to switch between processes instead of letting the processes run. On the other hand, if you have a quantum that is too long, then you will probably affect responsiveness. So if you take this example, if you have 50 processes, okay, and you look at the last one, and you are using this round robin scheduling, okay, and the quantum is 100 milliseconds, then you see that for this process to start, it will take 5 seconds. And this, of course, it's not a really responsive system if it takes 5 seconds before a process gets assigned to the CPU. So it goes from ready to running. Especially because you don't know it, but it might be that this process is actually the shortest one and it's IO bound. So actually running it in the beginning would not really change much for the others, but it would make a significant difference for this specific process. Something we can do is to do something a bit more accurate, or let's say to have different priorities, as the name suggests, priority scheduling for the different processes. Okay, this is based on the assumption, which is true in many cases, that not all processes are equally important, right? So we assign priorities to the processes. This we can do it statically before they are started, or this can be also done dynamically. So the priorities can change during the execution, and it can be the operating system that does this, or even the user that specifies the priority. And we can, of course, combine priority with the round robin. So it would look something like this. Instead of having a single list of processes, we can keep several lists, and each list has a certain priority level. Okay, here we can assume that the highest priority means it's more, so that the higher value for the priority means it has a higher priority. Okay. Then you can start by running, for example, in a round robin fashion. You can combine these two, the ones that have priority 4, and once all of these are done, you can start running in a round robin fashion the ones that have priority 3. If everything is done here, then you can move to priority 2, and so on. So if you think back at the example I made about the first come, first serve, and why it's not really optimal for giving a fair amount of resources and making all processes finish rather soon, especially if they can, you can see that this could potentially solve the problem, because you could put the processes that are IO bound in the list that has a higher priority, and then the ones that are CPU bound in the list that have a lower priority. Think about this, you will see that this would solve the previous problem. The last one is lottery scheduling. It's nothing different from what the name is actually saying. It's lottery scheduling. So it's an alternative to priority scheduling, okay, that allows you to control better how you give resources to the different processes. Each process gets assigned a set of lottery tickets, okay? It's not one, it's not a specific number. You just get a certain number of tickets, okay? And to decide which is the next process that should run, the operating system will draw a random, choose a random ticket, and who has the ticket is the one that gets access to the CPU. So you can imagine that if you want a process to run 50% of the time and other two processes to run each 25% of the time, then you can distribute a certain number of tickets accordingly to these proportions. And then on the average, this is what will happen when you use the lottery scheduling. So it's easier to map portions of resources to give to a process, okay? Because basically the portion of tickets you give to that